Unit cells and basic structures. So crystalline solids have a lattice with this regular repeating pattern. They form the pattern to minimize the energy. They don't do it on purpose to make pretty patterns. They do it to minimize energy. And there are several different arrangements that these particles can make, and it's going to depend on the relative size and charges of the different particles in the crystalline solid. So we look at what's called a unit cell. The unit cell is the smallest part of the crystal that we can repeat in 3 dimensions and get the entire crystal lattice. So in this simple pattern, you could take a larger cell, larger square here, and you could repeat that in 3 dimensions, but that's not the smallest. We're looking for the smallest one that we could repeat. And so that's going to be this one right here. If we take that and repeat it in all 3 dimensions, this is just showing 2 dimensions, but repeat it sticking out and going back, we'll reproduce the crystal from that one unit. Here we're representing lattice points with the circles. Those are going to be the atom, the ion, the molecule, whichever it has. And then they're connected just by electrostatic attraction or intermolecular forces in between. And we're always going to be talking about, usually we'll talk about a cubic unit cell, but there's also hexagonal cells as well. When we look at these, and like some other topics in this class, we're just kind of skimming the surface. And you may never need this stuff again, but especially if you're going into engineering, they talk about stuff like this. And so if you haven't heard it before, you're going to be lost. So when we draw these different cells, we're going to use different colors just to help us visualize what's going on. But the ones we're going to look at, each atom is identical to the other atoms. Okay, so even though they're different colors, we're just doing that to help us see what's going on. We refer to something called a coordination number. And that's the number of atoms that each atom is in direct contact with. Okay, so like in a neighborhood, the coordination number might be, how many close neighbors do you have? Well, I've got a neighbor on the left and on the right and directly behind me and across the street. So I have 4 neighbors that I'm basically in direct contact with, right? But other people might have fewer neighbors, or you could have more neighbors, I suppose. If you were in an apartment, you might have people above you and people below you as well. Packing efficiency is a concept we use to refer to the percentage of the volume that's actually occupied by the spheres, the atoms or the ions. If we have a high coordination number, we're going to have a greater packing efficiency. You can get more atoms into the same volume if they have a high coordination number. So here are 3 of the different unit cells. There's simple cubic, there's body-centered cubic, and there's face-centered cubic. And this is kind of an overall summary table. We see here the number of atoms per unit cell, the coordination number, the length of an edge in terms of the radius of the atom, and the packing efficiency. And so we're going to talk about each of these individually. So the simple cubic unit cell has 1 atom at each corner. So if we go back to this for a minute, we're looking at the center of this atom to the center of that atom to the center of this one to the center of that one, making a square on one side, and it's a cube that's repeated in 3 dimensions. So if we just look at the unit, this is what we have. In each corner, we have how much of an atom? 1/8. It's hard to look at, huh? This is 1/8 of an atom, and here's an 1/8, and here's an 1/8, and there's an 1/8. So on the bottom, we have half of an atom, and this top part, we have another half of an atom. So we have a total of 1 atom in the unit cell. We have 8 8/8, right, which is one atom. So 1/8 of each of 8 atoms. These atoms are going to touch along the sides. You see that? This atom is touching the next one right here. And so the length of this side, which is the same as the length of this side, is going to be 2 times the radius of the atom. You okay with that? So the length of the side is equal to 2 times the radius of the atom. In terms of coordination number, we're looking at how many atoms is it touching. So here we have one atom, and it's touching one on this axis, on this side, and on that axis on the other side. So maybe that's what the z-axis. And here's the x-axis. It's touching 2, 1 on each side, and the z-axis, 1 on each side. So it's touching 6 other atoms. Its coordination number is 6. The packing efficiency is 52%, and that would be calculated by taking the volume of the cube, which would be 2 pi, the quantity cubed, as the total volume, and sorry, I started with the bottom. If we wanted to calculate that, the volume occupied by an atom would be the volume of the atom, because it has one atom in it, right? So 4/3 pi r cubed divided by the volume of the whole cube, which is, each side is 2r cubed. And so that ends up giving you 52%. It's the percent of the volume occupied by the atom. Any questions? In the body-centered cubic, there is an atom in the center of the cube, and the other atoms are around it. When we just look at this chopped up version, it's a little hard to visualize. So let's go back and look at this guy. So here we have 4 atoms, and then there's one kind of sitting in the little dimple in between them, and then 4 more on top of that. And that's a different arrangement. That's called body-centered because there's one in the middle. So in the body-centered, we have the atoms touching along the diagonal from one corner directly across to the other. So this guy in the middle is touching this one and that one. And so directly across, we've got this diagonal that we can predict the size of. That's 4r all the way across. And so then you can do some geometry and find out that the length of the side is 4 times r over the square root of 3. So that's the length of the side. How many atoms are in this cube? How many complete atoms? 2, right? Because we've got the 8/8 plus the one in the middle. So we've got 2 atoms in the cube. So the atoms per unit cell is 2. Here, and this is where we've got the different colors. We're showing this one as gold, just so we can pick it out from all the purple ones, but these are actually all the same atom. So this one in the middle is touching 8 different atoms, because it's touching the ones on the corners, right? It's touching all of the atoms that are on the corners, so there's 8 of them. So the coordination number is 8. Higher coordination number, higher packing efficiency. So if you're packing fruit, oranges, and you want to minimize the size of your boxes, you want a higher packing efficiency. There's going to be less empty space, right? And then we have face-centered cubic. So here, we have an atom that's centered on the face of the cube. That's why it's called face-centered. So there's half of an atom, and half of an atom, and then over there we have half, and over here we have half, and up there we have half, and down there we have half. So we have 6 halves, right? So that's 3 atoms, And again, with the total of 1 in the corners. So there's a total of 4. These touch along the diagonal of one face, and so you can do the math and find that the length of the side is 2 times the square root of 2 times the radius of the atom. I do not expect you to memorize those. In this face-centered cubic, we have a coordination number of 12. And that's harder to just really see that that's going on, but it is. So we've got 12, and then higher packing efficiency corresponds to the higher coordination number, 74%. So we can do some calculations like this one. Density is related to crystal structure, because the density is the mass of the atom and in terms of the volume that it contains, right? But we don't generally talk about the density of an individual atom because we never do anything with individual atoms. But we do things with larger chunks of metal. And so the density is going to be related to the crystal structure. So here we're told that chromium crystallizes with a body-centered cubic unit cell. We're given the radius of the chromium atom, 125 picometers. So I should probably write that down. So the radius is 125 picometers. And it asks us to calculate the density of solid crystalline chromium in grams per cubic centimeter. What do? They gave us one stinking number. What is density? Mass divided by volume. Could we figure out the volume, say, of a unit cell based on the radius of the atom? Yeah, because we had equations for the length of a side for each of those unit cells. So let's go back. Oh, I've forgotten already. Short-term memory. Body-centered, yeah. Should be able to remember that. Body-centered, L equals 4R over the square root of 3. L equals 4R over the square root of 3. So the volume of that cube, the volume of the cube is going to be L cubed, right? Or 4R over the square root of 3, and that whole thing cubed. What unit do we want for our volume? Cubic centimeters, right? We're given picometers, so it might be easier to convert this before we cube it. What does pico mean? 10 to the negative 12, right? So 125 times, that's not what I meant to do. 125 times 10 to the minus 12 meters. All I did there was I plugged in what pico means, 10 to the minus 12. Now I want to convert this to centimeters. So meters on the bottom, centimeters on the top. Centi means 10 to the minus 2. And so when I stick this into my calculator, 125 times 10 to the minus 12 divided by 1 times 10 to the minus 2. I get 1.25 times 10 to the minus 8. You could do that without a calculator, but it's so easy to make mistakes. So there's R. So the volume of one unit is 4 times R, 1.25 times 10 to the minus 8 centimeters over the square root of 3. And I take that whole thing and cube it. So I'm going to my calculator, I'm going to do x to the third power. No, that's not going to work. I'll do the inside first. 4 times 1.25 EE minus 8 divided by the square root of 3 equals, so that's 2.88 times 10 to the minus 8, and then I'm going to raise that to the third power. So the volume is 2.40, we should have 3 sig figs here, 56 times 10 to the minus 23rd cubic centimeters. Whoa, yeah. Is it okay that it's so small?
Yeah.
Yeah, it is. Okay, so density is mass over volume. So we found the volume of one unit cell. 2.4056 times 10 to the minus 23rd. How can we find the mass? How many atoms are in one unit cell?
In that one, there was two.
2. So there's 2 atoms. Could we figure out the mass of 2 atoms?
Yeah.
Sure we could. Because we know how much 1 mole weighs, right? So I'm going to take 2 atoms,
51
and there's 6.022 times 10 to the 23rd atoms. That's 1 mole, and how much do those weigh? 51.9961 on the periodic table. One mole is Avogadro's number of atoms, and that weighs the number on the periodic table. So we've got 2 times 55.9961 divided by 6.022 times 10 to the 23rd. And this is also a really small number. Is that okay? Yeah, it is. It's 2 atoms. It should be really, really small. And if it isn't, we did something wrong. It's 10 to the minus 22 grams. So let's stick that in there. 1.8597 times 10 to the minus 22 grams. I don't know why I put 3. How many sig figs would that number have? I just kind of arbitrarily did that. Well, how about this 2 atoms? That's infinite. That's exact. And this one I wrote down with 5, and here I've got Avogadro's with 4. So this should be 4 sig figs. Okay, so 1.8597 times 10 to the minus 22 divided by 2.4056 times 10 to the minus 23.
Wouldn't it be 3 because you have 25?
This one is 3, but the mass would be 4. Then the ultimate answer is going to end up with 3. So I'm coming up with 7.73 grams per cubic centimeter. They've rounded it to 3 sig figs because this one had 4 and this one had 3. Is that a reasonable density for a metal? Sure. What if it was 77?
It's like the heaviest one. Probably not.
77 is not reasonable.
Yeah.
I think the most dense one is like 19 or something. But metals are more dense than water, or 21, something like that. Definitely less than 30, though. So 77 would be crazy. But 7 is very reasonable. So we can calculate the density of chromium. Not sure how that would be very useful in your everyday life, but there it is.
that only works for crystal structures.
You can only do that with crystal structures. You got to know what the crystal structure is.
If we have a question like that, will we be given some of those?
I'll give you those lengths. I don't expect you to memorize those. I think your brains are full enough. We'll stop there for today.